There are two major ways that we can calculate the standard free energy change, or Gibbs free energy. This is the change in free energy when reactants in their standard states are converted to products in their standard states. The standard state means 1 atmosphere of pressure, 1 molar if it's a solution, and 25 degrees Celsius. We can calculate delta G by using the standard enthalpy and standard entropy. Delta G will equal delta H minus T delta S. The other way is that we can calculate delta G directly by using standard free energy of formation values. Delta G will equal the sum of the standard free energy of formation of the products minus the sum of the standard free energy of formation of the reactants, much like we calculated delta H and delta S previously. The standard free energy of formation, or delta G sub F naught, with the subscript F meaning formation, is the free energy change for the formation of 1 mole of a substance from elements in their standard states. It gives a measure of the substance's thermodynamic stability. We can use these standard energy of formation values to calculate the Gibbs free energy for any reaction. You can find a full version of the standard free energies of formation of different substances online. This is just a short version of that chart. Notice that the values for any substance in their standard state has a delta G sub F of 0. You can think about this as like a thermochemical sea level upon which every other substance is measured against. So silver solid, aluminum solid, solid carbon, those are all in their most stable standard states. So they have a delta GF that's assigned as being 0. You also want to take note and be careful that you're looking at the correct state of matter. Water has a value for its delta GF if it's in a gas phase or if it's in a liquid phase. So make sure that you're also checking the states of matter when you're using these values. So let's look at the first way that you can calculate the delta G of a reaction by using the standard free energy of formation values. If we take the sum of the products minus the sum of the reactants, being sure to multiply by any coefficients of the balanced equation, we can calculate the delta G of any reaction, much like we calculated the delta S previously or the delta H last semester in Chem 1. In this example, let's calculate the standard free energy change and then determine if this reaction is spontaneous or non-spontaneous as written. Delta G, or Gibbs free energy, can be calculated by taking the sum of the products. So we're going to have 4 moles times the Gibbs free energy of formation times nitrogen monoxide plus 6 moles times the Gibbs free energy of formation for liquid water. That would represent the sum of our products minus the sum of our reactants. We're going to have 4 moles times G sub F for ammonia, plus we would have 5 moles times G sub F for oxygen. And that would be the sum of our reactants. Next, we want to consult the chart to figure out what the delta G sub F's are. 4 moles times our free energy of formation for nitrogen monoxide, which is 86.96 kilojoules per mole. Our units of moles are going to cancel, and we'll be left with kilojoules. Plus, we have 6 moles times our G sub F for H2O, making sure that we're using liquid H2O, negative 237.2 kilojoules per mole, minus 4 moles times our G sub F for NH3, which is negative 16.7 kilojoules per mole on our chart. Plus, lastly, we have 5 moles. And for O2, since that is how oxygen appears in its most stable standard state, the G sub F for O2 is going to be 0 kilojoules per mole. So our moles will cancel and we'll be adding together kilojoules when we calculate our delta G for this reaction. And delta G comes out to negative 1010 kilojoules. And since we got a negative value for our delta G, that tells us that this reaction is spontaneous as written. Delta G, or the free energy change, is equal to the free energy of the products minus the free energy of the reactants. If the free energy of the products is less than the free energy of the reactants, then delta G will be a negative value, which indicates a reaction is spontaneous. If the free energy of the products is greater than the free energy of the reactants, delta G will be a positive value and the reaction will be non-spontaneous as written, and would actually be spontaneous in the reverse direction. If we have a situation where the free energy of the products is exactly equal to the free energy of the reactants, that would mean delta G is equal to 0, and that reaction would be at equilibrium. We can use the equation for Gibbs free energy to estimate boiling points and melting points. When a phase change occurs, that equilibrium can only exist at one given temperature and atmospheric pressure. Anytime something is undergoing a phase change, it's an equilibrium process. The equation delta G equals delta H minus T delta S can help us estimate what that temperature is where that phase change will occur. We learned that delta G is equal to 0 when a reaction is at equilibrium. So we can plug 0 in to delta G and rearrange our equation. We'll have 0 equals delta H minus T delta S. And we can move our T delta S term by adding it to the other side, which will give us delta H equals T delta S. And then we can say that delta S will equal delta H divided by delta T by dividing both sides by the temperature. And lastly, the temperature can be calculated by taking the enthalpy, or delta H, divided by the entropy, delta S. This will give us an estimate of what that temperature is if we only know the enthalpy and the entropy. For the melting of aluminum, the enthalpy of fusion, in other words melting, is equal to 10 kilojoules, and the entropy is equal to 9.5 joules per Kelvin. Assuming that delta H and delta S are nearly temperature independent, calculate the melting point in degrees Celsius of aluminum. So here we have a phase change occurring. We have aluminum solid in equilibrium with aluminum liquid. And what's happening is fusion, or in other words, melting. We can use the equation delta G equals delta H minus T times delta S. But we're going to plug in 0 for delta G since this is an equilibrium process, which would lead us to 0 equals delta H minus T delta S. We saw if we rearranged that equation, we would get the temperature is equal to the enthalpy divided by the entropy. The values that are given to us in the problem for the enthalpy and the entropy would technically change by a small amount if they weren't measured at 25 degrees Celsius and were technically measured at whatever this melting temperature is. But we're assuming that they're nearly temperature independent and don't change very much. So we can substitute them into this equation. We're going to plug in 10 kilojoules for delta H divided by our delta S. But notice our delta S has units of joules per Kelvin, so we're going to need to convert that into kilojoules per Kelvin so that it'll cancel with our delta H. That would be 9.5 times 10 to the negative third kilojoules per Kelvin. This will give us a temperature of 1052 Kelvin. In degrees Celsius, we would have 1052 minus 273, which is about 780 degrees Celsius for the melting point of aluminum. For the phase change, bromine liquid to bromine gas has an enthalpy of 31 kilojoules and an entropy of 92.9 joules per Kelvin. Assuming that the enthalpy and entropy are nearly temperature independent, calculate the normal boiling point in degrees Celsius of bromine. We're going to plug in 0 for our delta G equals delta H minus T times delta S. Rearranging, we get the temperature is equal to the enthalpy divided by the entropy change. So we can solve for that temperature in Kelvin. Our delta H is 31.0 kilojoules, and our entropy would be 92.9 times 10 to the negative third kilojoules per Kelvin, making sure to convert it so that our enthalpy and entropy have the same units of kilojoules. This gives us a temperature of 334 Kelvin. To get our temperature in degrees Celsius, we take our temperature in Kelvin and subtract 273, which gives us 61 degrees Celsius as the boiling point of bromine liquid going to bromine gas. Next, we're going to look at something known as free energy diagrams. Free energy diagrams are used to show how the free energy, or that available energy, will change during a chemical reaction. We'll look at the free energy diagram of a non-spontaneous reaction and the free energy diagram of a spontaneous reaction to see how they differ from one another. First, we're going to look at the free energy diagram for a reaction that is non-spontaneous as written. The reaction is the decomposition of N2O4 breaking down into 2 moles of NO2. On the y-axis, we have the Gibbs free energy, and on the x-axis, we have our reaction mixture composition. Over on the left, we have pure N2O4, and over on the right, we have pure NO2. Notice that the Gibbs free energy for our reactant, N2O4, is much lower than the Gibbs free energy for our product, 2NO2. In this case, we have a situation where the free energy of the products is greater than the free energy of the reactants. Delta G could be measured by looking at the difference between the Gibbs free energy of the products minus the Gibbs free energy of the reactants. And in this scenario, we would calculate a positive value for that delta G, since the products have a higher free energy than the reactants. It will always end up being positive. A delta G that was positive indicated a non-spontaneous reaction. Now notice where the low point on that curve between pure N2O4 and pure NO2 occurs. That low point occurs closer to the pure N2O4 or closer to the reactants. This dip where we're at that lowest point on our free energy curve represents the energy minimum. This is where delta G would be equal to 0. So at this location, our reaction is at equilibrium. And the equilibrium occurred far to the left, closer to the pure N2O4, which indicates that this reaction doesn't really progress forward very far before it even reaches equilibrium. So essentially, since it doesn't progress very far, we say that it's non-spontaneous as written, since very, very, very little products have actually been produced. Equilibrium occurs when the pressure is 1 atmosphere with only 16% of the N2O4 decomposed. So starting from our pure N2O4, we could move a little bit forward down the hill to reach that energy minimum, but we didn't move very far before we reached equilibrium. If we were to start with pure NO2, the reaction could progress very far in the reverse direction before it actually reached equilibrium. So this reaction would be spontaneous if we flipped it around and we wrote it as 2NO2 breaking down into N2O4. That reaction would occur spontaneous as written, since the direction that we're looking at is non-spontaneous. So when that energy minimum lies closer to the reactant side, essentially that reaction is non-spontaneous as written. It has a positive delta G, which also indicates that, and the free energy minimum is far to the left. In order to get your reaction, which is at equilibrium, out of equilibrium, either to form reactants and go backwards up the hill, or to start forming products, you would need some kind of an energy input or a shift in order to drive it away from that low energy point where equilibrium has been reached. Now let's compare the free energy diagram of a spontaneous reaction. We'll keep it simple. We have the reaction of A going to B. If we check out the Gibbs free energy of our reactant A, we can see that A has a much higher free energy than product B. So this is a situation where the free energy of the products is less than the free energy of the reactants. So if we were to calculate delta G, we would end up getting a negative value. That negative value told us we had a spontaneous reaction as written. The difference in the free energy of the products minus the free energy of the reactants would represent this gap right here between them, and we would end up getting a negative value. Notice where equilibrium occurs in a spontaneous reaction. The free energy minimum, where the curve comes to its low point, or where delta G would be equal to 0, occurs closer to where pure B is than where pure A is. So reactant A was able to transform into product B and produce more B than we have A left over before the reaction reached equilibrium, due to the free energy lowering of A. Once we reach equilibrium, we're now at that free energy minimum where the reaction doesn't want to change or shift anymore unless there was some external influence. But where we reach that free energy minimum at is now closer to the product side. So the reaction's actually able to proceed forward from A to B, producing some more of B, much more than we did last time where the free energy minimum was much closer to the left. Now it's much closer to the right. So this represents a spontaneous reaction as written. We can summarize the free energy diagrams. When delta G was positive, the position of equilibrium, or delta G being 0, lied very close to the reactants. Very little reaction actually occurred by the time equilibrium was reached. The reaction appears to be non-spontaneous, as written, going from reactants to products. When delta G was equal to a negative value, the position of equilibrium lied close to the products. A large amount of products were formed by the time equilibrium was reached. Very few reactants were left over at that point. The reaction appears to be spontaneous as written, going from reactants to products. When delta G is exactly equal to 0, the position of equilibrium lies between the reactants and the products. Products and reactants are present when equilibrium is reached. The reaction will appear to be spontaneous whether we begin with pure reactants or pure products. For the reaction given, is the reaction spontaneous under standard state conditions? And if not, at what temperature will the reaction become spontaneous? We were given the enthalpy of 98.8 kilojoules and the entropy of 141.5 joules per Kelvin. We have a positive value for delta H, which tells us that this reaction is endothermic. And we also have a positive value for our entropy, which tells us that there's an increase in disorder going from reactants to products. If we want to determine if the reaction is spontaneous or not, we want to calculate the delta G. The sign on delta G will tell us if the reaction is going to be spontaneous. We can calculate delta G by taking delta H minus T times delta S, making sure that our units are all correct. The enthalpy is 98.8 kilojoules minus our temperature, which is going to be 298 Kelvin. Our temperature is assumed to be 25 degrees Celsius at the standard state, which is what those superscript naughts represent. 25 degrees Celsius is equal to 298 Kelvin. And then lastly, we want to multiply by our delta S, which is going to be 0.1415 kilojoules per Kelvin. Our temperature had to be in Kelvin so that it will cancel with our units on our delta S. Our delta G comes out to being positive 5.66 times 10 to the first kilojoules, or 56.6 kilojoules. We got a positive value for our delta G, so the reaction will be non-spontaneous. Next, if we want to calculate the temperature at which the reaction will change from being non-spontaneous to being spontaneous, we want to plug in 0 for our delta G, because that's going to be where it transitions from going to a positive sign on our delta G to a negative sign on our delta G, which is what we need if the reaction will be spontaneous. So we can use the same equation, but plug in 0 for delta G. That will equal delta H minus T delta S. If we rearrange and solve, we can get the temperature is equal to delta H divided by delta S, just like when we calculated the temperature of the phase changes. And then using our enthalpy and entropy, we have 98.8 kilojoules divided by 0.1415 kilojoules per Kelvin. This gives us a temperature of 698 Kelvin, and that would be the temperature at which it would transition from being non-spontaneous reaction to a spontaneous reaction. So this reaction is going to be spontaneous at high temperatures.